moving from one region to another. When wanting to calculate the current, it's the charge over the time, and that's like the formula to get the current. If the charges follow a conducting path that forms a closed loop, the path is called an electric circuit, and that's what we're going to do today. We are going to do a series circuit and a parallel. Okay, I'm going to explain you the materials that we are going to use for this experiment. As you can see, this is called a breadboard. Here is where the the charges is going to flow, and this is essential for this experiment. If we don't have this, the experiment wouldn't happen. And then we need a wire. As you can see, it's two colors, a red and a black. The black is negative, and this is positive. And also we need a battery this is 9 volts for voltage. So with this and this, we are going to connect this to the battery and then this to the breadboard. So this is going to pass the voltage to the breadboard. And then we need some LEDs, which are light emitting diodes. In other words, they are one-way street. It means that it only flows in one way, the charge. And here, as you can see, one is larger than the other one. That means that the largest is the positive and the smallest is the negative one, and are different colors. And last, we need resistors, which they hold back the energy, so this wouldn't burn. And these are the materials we are going to use for this experiment.
Series connection. As you can see, we connect both of the resistors which have the same resistance. We have the LEDs in a circuit. They are connected equal, so it creates a circuit. So as you can see, if we connect it, it will turn on. But if I will be connected. If we remove one LED, you can see everything will shut down because all is a circuit. So if we remove it, it will shut down. In order to get the total resistance, we need to add every resistance of each resistor. Okay, the current in a series circuit is everywhere the same. So if we want to calculate the total resistance, it will be the voltage of the battery over the resistance of each resistor.
As we all know, in parallel circuits, the charges or resistors in this case are independent of each other when they're parallel. So if we were to take away this one, for example, the circuit will still work because it's in a parallel condition. However, if we take away this one, since it's not parallel with any resistor, the connection is going to go off. We can just take it off and see what happens. See, it went off because this wasn't in a parallel connection.
As we can see right here, we have a parallel circuit. The voltage drop is the same across each parallel branch. The sum of the current in each individual branch is equal to the total current of the circuit. We know that this is a parallel circuit because we can take away an LED and the circuit will stay the same.
As we all know, when we're talking about a series connection, the resistance is calculated simply by adding the different resistances. However, when we're talking about a parallel connection, it changes. To calculate the total resistance or the equivalent resistance in a parallel connection, you have to use this formula. First, 1 over R EQ, which is equivalent resistance, equals 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. And if you have more resistances, then you just have to add them all.
However, this is going to give you 1 over resistance equivalent. If you want to calculate just this part, you're going to have to do this to the -1, and then you are going to get resistance equivalent. As we can see, the series and parallel connections are not just a matter of equations. We can actually see real-life examples and applications. For example,
nowadays we can see the Christmas light.
in the refrigerator.
This was parallel and series circuit.